Good morning, everybody. Good morning. Nice day today. I just want to recap. We are sort of in the middle of our time. We've spent half of our time already, and we just want to recap what we've done, and then just show where we're going. Okay, so that you can see the connection between the story. So at first we started with classical mechanics, which was Newton's law, which was the second law of Newton was the important case, and we looked at Newton's laws, and then we derived from that, or arrived this idea that we have a Hamilton function, which is a function of p and x of the momentum and the position, which is equal to p squared over 2m plus v of x. So this was possible for forces which are given by the derivative of this with respect to x, with the minus sign. And then we went further and we said, well, let us take this and apply it to certain potentials. And the potentials we looked at was the potential which goes like a straight line, which was what? Potential for what? V of x looks like this. This describes free fall, yeah, body falling. And so we could look at this potential as saying the potential for the bouncing ball experiment. So if we have a certain energy, then this the particle or the ball would be stationary at this point, and we drop it and it falls back to the ground to where x is 0, and then it jumps up and down and so on, and it does that. So that was the first potential we looked at. The second one, which I only briefly mentioned, but let me put it here as the second one, is the box, where we have a particle in a box in one dimension. It just goes from the one corner to the box back to the other. So it looks like this. That is the potential. The particle is in here in the box, and it goes forwards and backwards. It has no potential energy here. The only thing that happens, its momentum is reversed whenever it hits the wall, in the same way as the momentum of the ball is reversed when it hits the floor. Okay, and the next one we looked at was the harmonic oscillator. So that is a potential that looks like this. It is x squared, k half times kx squared, and we could then look at cases where we have a particle, say, or say the little girl sitting on the swing there at some point, some height x or some point x, and then it goes over, and then it swings backwards and forwards and so on. No? And this case we studied a little further, as we did in this case, about what happens if there is interference of air resistance. And in both cases, our system was then not isolated, and we call that an open system. we look at the system which is isolated, we could look at the closed system, and when it is an open system, the object which we look at, which we investigate, which we write down everything, is not conserving energy. It's giving off energy to the environment. So it actually moves not like this, but it goes down to a lower energy state and so on. And the same in this case. So we saw that we have the possibility of introducing a force which is dependent on the velocity and which takes out the energy of the body which we are looking at to the environment. And this is not reversible. This is the important thing, and this is where the link comes. We talked about the error of time, that it will not happen that this thing will go in the opposite direction and move up and up and up. Because the reason being that there are so many states into which the energy is dissipated, is moving into. And the last point, then we did this in 3 dimensions, and we also looked at the three-dimensional force for a potential that goes like 1 over r. Say the potential K over r. That looked like this, and in general, and we then discussed how we can make this 3-dimensional problem an effective 1-dimensional problem by looking at the conservation of momentum. Now, this is about all we did so far, but I would now want to show you. Oh yeah, maybe we should just add one more aspect, and that is in all these cases. We developed an idea of how to draw what is happening, a specific language in which we do things. And we introduced something which we call phase space. And that is the space in a 1-dimensional problem which has x in this direction and p in that direction, and that we call phase space. And the significance of phase space is what? So what did we do in phase space to describe what these equations give us? Someone would like to? Yes?
We can specify the action P times X at every
yeah.
space.
But we did something very specific. We looked at this problem, and at that problem we drew certain things here. For instance, in the harmonic oscillator, we drew something like this. And so what we actually established was that the solution of these things are lines in phase space. So as a function of time, if I give you something like this, you can say X, I'm here at this point. I mean, this is a movement in phase space on a certain line. And at this point, I can read off what is the value of X and what is the value of P. So that is actually the solution of our problem. We present it in this way. We say this is the solution of the problem. So for every time you give me, I can say, okay, I'm there, and that is the value of x, and that is the value of p. And then at a short time afterwards, I know this thing is moving in this direction, say, then I know the x is a little less and the p is a little more. And so I can see how the system behaves. Okay? So that is typically something we do in classical mechanics. We can also introduce phase space in 3 dimensions. Then I can't draw it on the board, of course. But then there's a px, py, and a pz, and there's a x, y, and z. So I have six components, and they give me what we call phase space, and these lines here are phase diagrams. They're diagrams in phase space, and they give us a picture of what the solution of the equation is. Remember, we have the solution of differential equations underlying this thing, but once we've finished all that, we can write it this way. Is there a question on this? It's clear to everybody? Okay. Someone would like to comment on this, or nothing? Okay, so what then happened in quantum mechanics? We're starting with quantum mechanics. So what is the statement of quantum mechanics, which we discussed last time? Speak up loudly, everybody wants to hear.
We said that the motion of the particle is not deterministic as in classical mechanics.
Yes.
Quantum mechanics is rather probabilistic.
Yes.
So we can simply estimate the interval at which we can say the particle is at that time, not specifically say that.
Okay, that's right. And on the language I'm using here, what does it say? The language here? Beg pardon? Oh? Operators. Yes, but I'm actually looking for something else at the moment. What we say, we can't do that. We can't in quantum mechanics. We can't do that. What we've been doing all the time. It's not possible, because there is this so-called uncertainty relation. Delta x, delta p is of the order of h, which means I don't know that this thing is at this point. I can just say it's somewhere in this block. And in that block, the size of this block is how much? H. Yeah, it's H. It's a delta p times delta x. So the size of this block is H. And this is the thing Planck found out. He needed that for black body radiation to do the calculation for black body radiation, which we will do. We will do what he said. So what you, just without doing any mathematics or on, just philosophically thinking about it, space is not smooth. It comes in little chunks, little pieces, and each piece is is so big. So I can say this is not a smooth function, just everything going next. It is actually made up of little pieces like this. And now I can say how many, now I can count how many such pieces are there in space. So if I calculate the volume here and I know what the momentum of the particles is that move around here, then I can say there is so much space for things in this room. Now I'm exaggerating this a little bit because we'll do our counting much more careful than this. So what is the future? This is what we've done so far. And where am I going? And the future is now we're going to do these different things. Well, maybe not that one, although we could. But let's just do this and this and this in quantum mechanics, where we know we can't draw these things, but we want to develop a new language which will tell us how to develop that. And we started with that last time. By looking at this case, but we made life a little a little simple by making this infinitely high. So the box is very high. Things cannot get out of the box at all. It's very high. Huh? So we make a very high box. So the potential here goes to infinity there and there. And so what it actually means is the particle is really confined, all the particles are really confined to be within that box. And so we wrote down the Schrödinger equation. Well, let me put here the wave function, yeah, and then we have to write down here, okay, let's do it again step by step. E over E times psi, huh? And this is a function of x. This is because we are working in the Schrödinger picture. I said we could work in other pictures, but we work in the Schrödinger picture. And this is and we have to solve this equation on the interval 0 to L, and outside that interval psi must be 0. And then we can just write this a little differently. Let me do that first. The potential is 0. The particles, they move here. The only thing that happens to them is they hit the wall. Huh? That wall is this potential. This potential guarantees that. You see, I'm looking at this equation. I only write down for.
What does the function of the potential look like?
The potential is, well, if you want to write it this way, it says V of x less than 0 is equal to, now mathematicians won't like this, but I'll do it nevertheless, is infinity. And V of x greater than L is also infinity. And V of x between 0 and L is 0. That is the potential. So it's something that moves freely, but it hits the wall. And that's not such a bad approximation for a particle which you confine in a box and you don't do anything to it. If you put down an electric field across it, then it would you would have to put in a potential like that inside the box and so on, but that makes it more difficult, and we won't do that. We will just let it move in this box forwards and backwards. And so I will write this now as is equal to k squared times psi of x, where k squared now is equal to 2m now let's make this a plus here, and so I take the case that in there, so I take this equation and I divide that by h bar squared. So I have the expression E is equal to h squared k squared over 2m, which looks similar to what we already know, like p squared over 2m, and I will write it this way, and I will say p is in fact h squared, h bar k. H bar k. So the momentum is h bar k, and the energy is given by this expression. Yes? I know you're a mathematician, but oh, they switched. Oh, sorry. Thank you. I thought you were worried about my way. No, thank you very much. Okay. So we did this, and we said psi is equal to some amplitude sine kx, and this has the right value at 0. The amplitude is 0. So we want to, we're looking at the particle in this box, and I'm writing now psi, and we want it to be 0 because it's not going in there, and then we want it to be 0 again at the value L. So to be 0 at the value L, we get k times L must be equal to pi. Or we could have k times L in general is equal to n times pi. It goes to 0 every time when we do this, and so we have a solution of this. What I said was an eigenvalue problem. For those who do not know what an eigenvalue problem is, this is an eigenvalue problem. These are the eigenvalues. These are the values at which solve that equation with the boundary condition, and if we put in this value of k, those are the eigenfunctions. the eigenfunctions of this problem. And so we can now look at how these things look. The eigenfunctions look like this. This is L. And the next one, this is again 0. But the next one I will draw, it looks like this. And the next one, these are repeats, sort of. Looks like this, and so on. So you can draw all these lines. And so this is the way the eigen functions look. And the eigenfunction now is a possible state of our particle which we are looking in. It can be in that state. It can either be like this, or it can be in that state, or it can be in that state, and so on, and it can be in any of those states. So this is the basic idea of quantum mechanics. These states have different energy, of course, because if I put that in here, I must put in Kn, so I will get an energy spectrum E of n, which is times this squared, and this is also squared. So these are the energy values where the particle can be in. And so I will now do a little aside and say I have this state. This is now E1. So how many particles can go in there? So in general, as we have discussed, this is a state for one particle. So one particle can be in that state. It's a state in which we can have a particle. And then we have a particle in that state. We have a particle in that state. Now this is assuming that we can only put one particle in each state. And here there are two new things which come into quantum mechanics, which you cannot know, but I'm telling you now. The one aspect is that if I have a particle with something called spin, you want to say something?
I just want to say that these states are for one particle, because I consider n for one particle.
Yes.
So E1, E2, and E3 does not represent many particles, only represents the states, the energy that this particle can
Have.
be in.
Yes.
So in this case, it can be, we can't deal with many particles. So only one particle, and assumes different energies with different states.
Yeah. Okay. So that's a fair comment. The comment is what he's saying is I'm jumping, and it's true. I'm jumping. If I have one particle, maybe we should restrict restrict our talk for the time being to just one particle. That's what this equation is for. What I was trying to jump to was if I have two particles, the other particle has the same equation, and the next one has the same equation, and I look at all of them together, and then I can see how I put it into the different places. But let's stick to one particle. It's a good idea. And so this thing has for one particle is one possibility. The only thing I just wanted to add is that we are just looking at the motion of this particle, but as it happens, if it's an electron, for instance, it can have spin, and which is a quantum number we have not discussed yet. But this spin can be up or down, and so that would make this two possibilities, and this would be two possibilities, and so on. But this is additional information. And also well, if we have only one particle, the other comment I would save for later. What I want to know now from you is, if I give you a value of n, how many states are there? Say n is 100. How many states are there with n is equal to 100? How many states? I say, No, but just the value. I say the energy is so that I put in 100 here, so I get E of 100. So how many states are there? The n is equal to 100.
99. We'll start from E0.
No, but I'm looking at this specific energy.
Only assume two particles.
That's right. So there's just one state, except for this additional thing of having spin up and spin down. So if I put in n is equal to 100, I ask you how many states there are, you tell me, well, there's one state for n is equal to 100. No? And if I put in 200, you say, well, there's one state with n is equal to 200. No? Okay? So that's simple. But now we are going to make it a little more difficult by saying that this box, which we are looking at, is a three-dimensional box. So we are having particles going this way, and particles going this way, and particles going that way. Yeah? In three dimensions. Or a particle can go this, one particle going this direction, or that direction, or that direction. So then we have, you can repeat this, you can do this for, well, I probably don't need to do that, but let me just do that. So you have actually a function which depends on x, y, and z, and this differential operator has dx, dy, dz, and we have actually three equations next to each other. So that one, and we have another equation that goes like h squared over 2m d2 dx squared dy squared of y, and it's again e psi y, and so on. No? So and then we can get a k which is associated with the x direction, we get a k associated with the y direction, and we get a k associated with the z direction. So in general, if now you must please stop me if you don't understand this. It's not that difficult. So if you don't understand it, I just didn't explain it properly. But if I do this in 3 dimensions, I will have an E, which I will call a total E, which is h bar over 2m pi over L squared, and then it will be n1 squared plus n2 squared plus n3 squared. Do you understand? So I'm doing this whole problem in 3 dimensions. I'm assuming they're the same. Yeah, they're the same. Huh? It's a cubic box. Huh? If not, then they are. And so now I can ask you this question again. If I say n is equal to 100, this n, how many states do I have? One. No. No. So I have you can think of it already in 2 dimensions. If you only have 2 dimensions, it's also already it's much bigger because the value of n. So the problem which we actually generated in this discussion now is that we have nt. Well, maybe this wasn't the best way to write it, but we have nt is equal to n1 plus n2 plus n3. So we have a number. Sorry, this is maybe not the right way to write it. I write this en1. E is a function of n1, n2, and n3. And so a number of these states will have the same energy. Okay? And so the question is, in how many ways can I do this? 6.
Every dimension has 2 states.
But if I fix this number here,
and one can't be 0.
so that must be, it can be 1, and it. So I want to say nt is 100. So then I can have 1, 1, 98, 1, 2, 97, 1, 3, 90, so on. So I can have all these combinations. Huh? And so we're not really worried about 100. We are worried about very large numbers. So the question is, how many?
6 states. Every dimension has 2 states. So the possible states is 6.
Okay. I think we will just have a little exercise. And the exercise is for you to count those states. And I can maybe help you a little bit by saying we have these 3 directions, and we want to know how many states are there in this. Well, there are 2 things we want to know. How many are there in this total volume here? And how many are there in this space around in a rim? Say I want to look between 100 and 105 or 110 or something. I want to count the number of states which lie in a certain value of. I think you must go and do some. So you sit together in a group.
Every state has renewable space. Every state represents renewable space. So I can make it 27. These states, are we looking at the energy levels or the states like this you're showing there?
Yeah. Well, I think there's a good question here. I was a little bit confusing. We look at K values, which are given by N1 plus N2 plus N3 times pi over L. We want to look, I'll give you a value of K, which is determined by NT times pi over L. I'm looking for that number. How many states are there? Well, actually, no. I'm looking at the number of combinations in which I can get a fixed number of NT within some little proportion. Say it needn't be. If I make it a fixed number, then it may vary. You may not get that number exactly or so. But to make a little band of it. Make it between NT and delta NT. Okay? So this is not a physics problem, this is a mathematics problem. The question is, in its very simplest form, is I give you a number, say 100 or 1,000 or 1,000,000. I'll give you any number. I'll give you such a number, and you tell me how many times to achieve that number can you choose N1, N2, N3 differently. So if I give you a number of 4, it's very easy. Yeah? It's 1, 1, 2, 2, 1, 1, 1, 2, 1. 3 possibilities. Okay, that's the answer. No, we start from N. We start from 1. N starts from. Okay. So this is the question at the moment. Can we continue? I think many of you took different. Many of you took different approaches, and maybe I'll show you my approach, which is sort of the physicist's view of doing things, so what I would say is I plot N1 here, and I plot N2 there, and I plot N3 there, and if I and any point, and then I draw I draw a sphere around all these points, and that condition of N1 plus N2 plus N3 falls in this must fall in the sphere, which has the radius of this value N total, which I defined. That these are all the points. Okay, they fall within that. So I can count those quite easily by just using 4 pi over 3 nt to the power 3. That is the whole sphere. But now I have also counted the negative ones. And I shouldn't do that. I should only count the positive section of it. And so I have to divide this by 8. Well, if it's a circle, then there are 4. If it's a sphere, there are 8 possibilities. Huh? Okay. So I divide it by 8, and this would give me those which are in the positive segment of all these cases. And it would, of course, change a little bit with NT if depending on whether I hit one here exactly or not, and so on. But this would give me a good result of what the number of states are within there. And now if I just want to say how many are there for the value NT itself, then I would just say, well, I look at this equation with NT plus 1. I put in NT plus NT is equal to, say, N plus 1, and I put in NT is equal to N, and I subtract the 2, and that gives me the rim around this. Gives me the number of which have the value NT itself, and not just every number up to NT. So this is all the possibilities up to the value NT, and this is and if I differentiate this, basically I will get 1 over 8 4 pi n t squared times delta n t, which basically says how big I make the rim, whether I count them exactly or I count between 100 and 105 and so on, just the size of the rim. And so this is the number of states which are in that rim up there, which for large numbers of n is quite a large number. And I think some of you got this right by doing it by counting the states, by having basically, if you had an n squared term, then you are right. And I presume that number came out correctly as well. So if we look at this now, we know that this is K. K looks like this, and I want to now know what is the number of states which lie between K, some value of K, and K plus delta K. So what is the number of states between which I have between K? So I just have to multiply this thing with n over pi, pi over L. So the number of states in the interval k and k plus dk is equal to pi over 2, and then for each k I must put in for each n I must for each k I must put in a pi over, no, I must do it the other way around, L over pi. And I can do that for here and for there. So this is to the third. And then I have there k squared dk. Is that correct? Check me, please. 4 pi k squared dk. Yeah, that is the number of states that fall into. So what I've just done is I've replaced the n backwards with the k, and so this is the number of states I have. And so if I write down the number of states in the momentum interval, so we write this like this: the number of states p of momentum p and dp. So I still, the only thing I still have to do is I have to change for k, I put in p and I divide by h bar, and then I get let me say L to the 3 is v cubed. V is L cubed, is v, is the volume of the box. And here I get p squared dp, but I have to put in h bar cubed. I have to divide by h bar cubed because I'm going from k to p. I have to put in 1 over h bar cubed, which means 1 over h cubed, and then 8 pi to the third. And now I can divide that out, and I get I don't think that's correct. The answer, I made a mistake somewhere. Have you checked me? There's something wrong here. Oh no, it's correct. That's 4. And so what I get here is equal to V times 4 pi p squared dp over h to the power 3. And so what you see is in our phase space, which is a space of P and X, what is the volume of this phase space we're looking at? Is the volume in the x direction, because we're now looking at the volume in the x direction, and we're looking the volume in the p direction. In the p direction, we are looking at the rim between p and p plus delta p, and we now have to multiply that with 4 pi to give us the rim. So we have going up to p, and then this thing is dp, and so we're looking at how many states are between p and dp. So that is all the states, 4 pi p squared times dp is basically for the possible values of p, times the possible values of in the x direction, which is L cubed. And so this is a volume in phase space. Remember, phase space is xp, and we're looking at phase space in three dimensions. So what is the volume in phase space? It's the volume of the box in x, y, z direction, which gives the volume. And it's the volume in the p part of phase space, which is a section of it. Anything between p and p plus delta p. Okay? So what we see here is we write down the volume in phase space, and we divide it by h to the power 3, and that is a unit volume in phase space, which I said before already. In the one-dimensional case it was h, now we are in three-dimensional case, so it becomes h to the power 3. And so we have a volume in phase space divided by h to the power 3, which gives us the number of states. And is that clear? Is it clear to you? Okay, then ask a question, please. Then, well, they are initially when they're like we did the problem, but we're looking now at very large values of n, and it doesn't matter. That is actually something you can do, is look at this formula which I used here, and check it as you increase p, or the value of n. If you increase it, you will see this formula is a smooth formula, while if you do the calculation with integers, it would be step thing. And so if you go and calculate this for large numbers of n, these steps would be smoothed out. Okay? You're also quiet. I want to know whether you've understood what we've done. We've tried to count number of states. And why is this important? This is important for anything you do in statistical mechanics, and it is very important for doing the black body radiation. And the reason, and I'll come to that very quickly now, if you think of, say, I have a box of chocolates, and I put it down here, and I say how many, each of you can just pick one chocolate. So then I will distribute these chocolates throughout the group. Okay, and so you and if you all take just one, and you don't, then the average number of chocolates is one per person. In the same way, if we look at a system which we want to disperse among many states of possible states wherein it could be, and then we say we have to know how many states are there available to be filled. How many states are there which you could occupy? Like if I could bring a box of chocolate, I need to know how many people are here, so that everybody gets one. No? So I need to count the possibilities where I can put them. And this is the same thing here. So we look at the system, and at the moment we're still talking about one particle. But we just want to know how many possibilities are there for this one particle to be in. And that, in terms of normal phase space, as we have defined here, is given by this number. I think someone quite early here was telling us that I don't know who it was, remember, that there were infinite number of pieces of in his paper if you cut it smaller and smaller. But this is a bit of a different argument. But let me just say, the thing in quantum mechanics is the space comes in pieces. And there's each, and the particle can occupy one of these pieces, one of these. And I want to know how many such states are there. I drew this earlier when we had our phase space. I said this is where the particle can be in that box. And so I said we can divide the whole plane up, the phase space plane up into little boxes. And then we know how many states there are by taking the area of this phase space and dividing it by the size of a unit box. And what we here have is that the unit box in a three-dimensional problem is not h, but h to the power 3, because there's a delta xp, delta yp, delta zp, and there's a delta x and the delta y and delta z. So the unit box is a six-dimensional unit box, and its value is h to the power 3. And this realization that this is the case made it possible for Planck to calculate the blackbody radiation.
From that general form, how can I get the number of states for each axis, like the number of N1, N2, N3? So if I use that formula, the simplest one, 1/8 divided. So I want to have the number of states at each axis on 3 dimensions.
Well, if I stay in on a one-dimensional line, then I just have a state for each. If I stay on a one-dimensional line, I just have a state in each little box. Okay? So there's one here, there's one there, there's one there, there's one there. But if I if I go into a two-dimensional case, I have x and y, then if I look at this here, then there are, I look at I want to see how many are in this plane here. Or let me put, well, so the point is any point in a two-dimensional space, this thing is has a n1 and an n2 value. So if I look at this area here, the number of boxes I can fit in there, the number of boxes I can fit in on this line is just linear, and there it becomes a square.
I was trying to, because I know n t is the total number. If I'm in three dimension, n t is equal to n1 n plus n2 n3. So now I want to have an idea, based on this general formula, to know, okay, what's going to be the number n1, n2, n3, something like that. So how can I derive from that general formula?
So this is what we've been doing. We've said nt is if I make these two 0, then nt is this size, but I can switch it, but then I can make this less and I make this more. And so in that way I get an area. And if I do it in 3 dimension, I get a volume. Nobody understands it.
Maybe this question is based on, in our final formula, there is no the total NT, so that we can maybe isolate that we are in N1, we are in N2, we are in N3.
We are saying we are, in this total formula, we are saying we are going up to we are from a value P, which has 3 components, Px, Py, and Pz. And the one component is is N1, and the other is N2, and the other one is N3. So this P, which I wrote here just as P, is the length of this vector P. So maybe that is the problem. So we have a vector P, which is given by P1 plus Px. Px plus Py plus Pz. Okay, and then we call the length of this vector, we call P, and this is what this P says. It's the length of the vector. Huh? So that's maybe confusing. That for any length of that vector, and that is associated to the nt basically, and of that length, and then that length plus a little bit. How much are in that area there? And this is the number.
I'm getting confused, but I need to ask, for example,
Yes.
if we're given that nt equals to n,
Yes.
how can you find the number of states using this formula?
This formula. No, I use this formula. I was just
When do we use this?
when we do use this formula, just now.
The question is, we were working on if you had given an NT, how many ways could we arrange N1, N2, N3? And people were coming up with a formula in terms of N minus 1 times N.
Yeah.
So I think that's maybe, we're looking at just the total number of states.
Yes. Yes.
For a smaller N.
Yeah, but also for a million. NT is equal to a million. We want to know for or Avogadro's number. We want to know it for really big numbers. So this 100 was just to keep you confined to something small.
We go over that. I think that's what the question is. I think that's part of the confusion.
Yeah.
We're working it out for N equals 3, N equals 4. We're trying to find a formula
Yes.
in terms of N.
Yes.
And then before we got to this.
Yes. But then so that's a good comment. You were working out how many. We were working out this something which I wrote like this, and you have an answer, and you can compare it to this answer. This is the number of states up to 100. So then that is if there's there's one state, or there are two states, or three states, all the numbers up to 100. And so now I want to know how much are there between 100 and 101. Okay? So I will. So I'm looking at this differential between 100 and 101. So it's delta NT is the rim, and up. So between 100 and 101. This is what I'm looking here.
I mean, this is an integer number. If you look at N plus 3, the total number is 1. N
Yes.
plus 6, the total number is 10.
Yes.
That's not an integer number. I think that's where the confusion.
Yeah. Okay. So now the thing is, okay. Do you want to explain it, or should I explain it? You come and explain.
What we've been working at.
Yes.
I've been walking around
Yeah.
with integer numbers.
Yes.
And now I know when we look at big N, we can do this, but how do we relate that to?
We take your result, which you have derived, and we put it in here. So we make delta NT is equal to 1. So we're just looking at the number 100. You see well, okay, maybe I should do it this way. You've calculated it for 100, and you have a formula. Something like NT minus 1 and NT plus, I think I've seen such formulas. I don't know, divide by 2 or something. You've got formulas like this, which are, and now you can calculate that with NT is equal to 100. Now you can calculate that same thing with 99, and you can calculate it with 98, and so on. And I take all of these together and I sum them. All these numbers I sum them. And that is this answer. Now what Emma says is, but that would be a real number, the whole number, integer. This will not be an integer. This is an approximation to that, and you're welcome, and it would be nice if you actually do that. Compare your result with this approximation. And what I was saying to someone else earlier, that if you look as a function, there's the number of states, number of states I plot here, and here I plot this NT. then as I go, it'll look like this, sort of steps going up like this. And if you make NT bigger and bigger, the steps will be less and less important. There will be still steps, but I can draw a smooth line through that. Okay? And that smooth line, which is the number of states, that smooth line will be equal to this. Okay? And you're welcome to. I would actually appreciate if somebody checks that. I've done it many years back. I haven't done it now again. But that is actually the smooth line would go. The smooth line would go like this, and that is for the sum of all these. NT from 100 to down. But now we're looking at the value, just the number 100, and not the sum of all these. And then I have to differentiate that, and then I can choose a delta T, NT, which I can make 1, then it will be 100 and so on. But if I make this too small, the number will oscillate very much, because what I'm going to do now, I'm going to differentiate this funny curve here, and I'm going to try and find how it changes its gradient, and that would be still more irregular than the curve itself.
But n cannot assume anything other than integer numbers, because this is a periodic function which only either 1 or 0, 1 pi or 0 pi, 2 pi, 3 pi. How can it be delta n, for example, 0.1 pi?
You see, we're going from the description of a discrete spectrum, of a discrete mechanism, to something which is large, and then it starts to look continuous.
Yep, the space that we are talking about, the h or the h square or the h cube, that's what we try to look at a large scale. But I mean the function that we are really, the k or the p.
The function I was saying will not look like the one I wrote here. You would say, no, that's wrong.
Not exactly. I mean, how can I suppose that there is a delta nt? There is no such a delta nt, because the difference of the shell, the outer shell of n equals 100, and the one before it must equal 99.
Okay, so let's make delta nt
Equals 1.
an integer.
Must
Okay.
be an integer.
Let's make it an integer, if that would help you. Huh? Okay.
It's
Yeah, we either do between 100 and 101, and we do the sum, and we can make it between 100 and 102, so that integer could be 2, or it could be 3, or something, and you count the number of states in that. And that you can do. Huh? So I'm not insisting that you can make it an infinitesimal quantity. So think of this as an integer.
I mean, it must be an integer.
Okay, it's an
It's
integer.
not a special case. I mean, because the function itself is a periodic function.
No, no, it's true. But the thing is, we are approximating a result which looks like that.
This contradicts with the first idea of quantization. Energy, for example, E1, E2, E3. This is the whole idea of quantization. How can I just approximate it?
We are going from a system where the small numbers are important, whether it's 1 or 2 or 3, to the place where we have 100 million or 100 million and 1 or 100 million and 2.
100 million 1 and 100 million 2. They will be the same function will be applied. I mean, we have to apply the same formula for k and the same formula for e.
Yes.
Which includes a sine and or a cosine.
Yes. Yeah. So I grant you what you say. That is that if I say this is a continuous number, that is an approximation. That cannot be the real answer. Okay. But what I also say, it's a very good approximation when the numbers become very big. Okay. Okay. Yeah.
How can we find certain systems within counting number? How can we find the user states based on the part of the system?
Of the?
The particle, basically the particle.
Yes, we're looking at the moment, and Ibram has confined me to do so. We're looking at the moment at one particle. Okay. I was mixing up my language in terms of one particle and many particles, which we will do eventually. I will mix it up. But he was right in saying at the moment we're looking at one particle. Huh? And we're looking at the number of states which this one particle can have depending on its momentum. And if the momentum gets higher, the number of states which the particle can have increases like the square of the momentum. Okay, and remember this h cubed is an extremely small number. So anything we're looking at is these are very, very large numbers of states we're talking about. As you will all know from just looking at Avogadro's number of so on. I mean, we're talking about really big numbers. And the reason these numbers are big is because of this h bar, which is, this h cube, which is very small. Have we resolved some of the problems? Some. And some are left? Yeah?
What will happen if that constant goes to zero?
H is a fixed number. It's not close to zero. It's a fixed number. So we're not moving it. Okay? Yes?
I still don't give you an explanation on that formula. Because if we add this, we're saying we're getting an integer value, but that will not be an integer value. I don't get the explanation.
I say this is, you see, if I ask you something, this number here with n is a million, nt is a million, and I say work it out for me, and you work it out. It goes like 10 to the number is 10 to the power 12, huh? Because 10 to the power 6 squared is 10 to the power 12. Huh? That's how big that number is. Huh? And you and I say I want you to write it down, all the numbers up to, so that it's an integer, up to 10 to the power 12 numbers. Then you would say, no, you don't want to do that. Huh? You will give me the first order of magnitude. Okay? You will say, I will tell you the first 2 or 3 numbers, and then I will say times 10 to the power 12. Huh? Okay? And this is what this formula does. It says that you have these numbers which are integers, but they're very large, and I'm not going to write down those integers. It's up to the 12th figure. Or for that matter, in very many cases, it's much bigger than that. But whatever. I'm not going to write all that down. I'm just saying how many about. You would say, well, maybe 10 to the power 12. Huh? Okay? My formula will give you that. Okay?
Just an estimate.
Yeah, just an estimate. But an accurate estimate. Okay? I think we can. Maybe you can talk to me and to the tutors and so on. And I think we must step off this at the moment. I wanted to write down. Maybe I can still do that. I just want to write down the equation. The equation for. We have the number of states here. Yeah, let me do this quickly. We have the number of states there in a momentum. And now I will just give you the formula for energy for a photon. And energy for a photon. I want to, just for the people who do the black body radiation, I just want to make this a useful result. So I have an energy of a photon. In general, the formula for the energy is m squared c to the 4 c squared, okay? So, but the mass of the photon is 0. So for photon, I have E is equal to PC, okay? And so I have P is equal to E over C. And we already know from the photoelectric effect that that energy comes in packages of h bar omega over c. Yeah? So this is what P looks like, and so we now want to just put it in there. So we want to have the number of states of a photon between omega and omega d omega in a small interval, the number of states. And so we just put that in. So it is this equation here, which is V times 4 pi, and then I will get h to the power 3 omega d omega squared over h to the power 3, but this is another h. So I can change that h bar to this h if I divide by 8 pi squared, cubed. And then this becomes h, normal h. And so I can cancel to the third, and I can cancel it with that one. And so I... C cubed, okay? There? Cubed. There's one coming from, there are two there, and there's one from there. Yeah. And so let me write it in the standard form, and then you can just check the standard form. Oh yeah, and then there's one thing I've just mentioned briefly. The photon has, apart from being just a particle that is an energy packet, it also has polarization. You all know photon is polarized. It can go around this way, and it can go around this way. Okay, we are already finished. So I'll multiply this by 2. These are the 2 polarization directions, and then we get there's probably a pi squared. C to the 3rd. Let's just check whether that's a pi squared. Looks like pi squared. Huh? I have a pi here. That must be pi squared. Okay, so this is the number of states in a photon states in an interval omega plus d omega. And those who have worked on blackbody radiation will have found that at some point they must multiply by the number of states. And they would have found a formula like this. Maybe it wasn't omega, maybe it was nu, but that is related to omega, the frequency. And so that is the number of states used for a photon cavity or something. I hope you understood some of it, and I hope you discuss a bit among yourselves, and I hope you will ask us questions about it.